Okay, in this video we'll be discussing Organic Skills Training OST Exercise 3, Question 1. Okay, so in this case we are looking at this reaction scheme. We have an ester, okay, in fact 2 esters side by side, and then you realize that from this fragment, this ester with 1, 2, 3, 4, 5 carbons, right? They're down to 1, 2, 3, 4. Okay, so it's quite obvious that it's going to be involving hydrolysis of the ester linkage to lose 1 carbon. So it happens that there are 2 ester linkage here. So naturally, I will consider doing something to break down ester, and then you may be wondering, right? What will happen to the ester? So let's take a look. Alright, so if you break this bond, you get your carboxylic acid fragment. So this one here will form a carboxylic acid. Alright, the remaining fragment here will form your alcohol. So let's take a look at what I have over here. In this case, I have a secondary alcohol at carbon number 2. Alright, if I number this, 1, 2, 3, 4. Alright. Okay, let me just change the numbering. One, 2, 3, 4. 1, 2, 3, 4. Okay, and then the secondary alcohol you can see is basically your ketone, and your primary alcohol, it becomes your carboxylic acid. So think of a condition that can result in the breaking of ester at the same time causing an oxidation of your primary alcohol to carboxylic acid, secondary alcohol to a ketone. So in this case, it is going to be quite obvious that we are going to use oxidizing agent. Example, potassium dichromate. In this case, we have acidified condition. So why does this cause the hydrolysis of ester? The acidified medium and the heat will cause the ester to break. And then subsequently, the acidic potassium dichromate and the heat will cause your secondary alcohol and your primary alcohol to be oxidized to ketone and carboxylic acid respectively. So you must be wondering, what's the other side product? The other side product is actually this carbonic acid. You can take a closer look at the formula. It's H2CO3. It's essentially water and carbon dioxide, alright, dissolved together. So in this case, when you do oxidation using dichromate in the acidic medium with heat, this will result in both acidic hydrolysis of ester, so that's the first part, followed by the oxidation of your alcohols, secondary to ketone, primary to carboxylic acid. Okay, so that's question 1A. Okay, for those of you who want to copy down the answer or the explanation, please pause the video now. Okay, moving on to 1B then. 1B looks a bit more complicated. In this case, we have 7 carbon organic compound, and then we end up with 1, 2, 3, 4, 5, 6 carbons. Alright, so in this case, you realize that it's going to involve a step down reaction. Now, you must be wondering, where does the step down occur? So in the reaction scheme, it's given to you the number of carbons, 7 carbons over here to 6 carbons, which means the step down likely occur in the last step. Alright, so let's take a look at what some of the possible reactions that it can undergo. We have an halogenal alkane over here, and halogenal alkane, you may be wondering what kind of reaction it can take part in. So if you look at this compound, alright, one thing is that you realize that it's from a ring, then it became an open chain. So it must involve some breaking of the ring. Alright, So again, it must involve some breaking of the ring. This will give me an idea in terms of how I can break the ring. I will therefore involve an alkene. So my first proposal, okay, will be to involve an elimination reaction. I remove the Cl and the H to form a double bond here. Now some of you of course will be asking, there are two carbons with adjacent hydrogens. Why did I choose to eliminate this hydrogen? Alright, it turns out that it's guided by this thinking that I need to do a step down reaction. So a step down reaction, right? There are only a very few step down reactions that you can think of. One involving alkenes, alright, CC double bond. If you recall, we have a terminal alkene, we break, and then we get a step down reaction, right? Or we can make use of our iodoform. So in this case, it's likely I'm going to make use of iodoform, which means I will need this particular structural group. Okay, so as a result, I need C double bond OCH3. You notice that I strategically place my alkene such that I get a CH3 here. When it breaks, I'll get my COCH3 over here. Okay, so how can I do elimination of your halogenate alkene? I'll consider doing alcoholic KOH with heat. This is basically elimination of a halogenate alkene to form, so the H and Cl comes out, alright, and you form a double bond between the two carbons. Then subsequently, to get an open chain from a ring, naturally, as I mentioned earlier on, we will involve the breaking of the CC double bond using acidified KMnO4 heat. This basically cleaves your alkene up into this open chain. So at this juncture, it's just our postulate. One important way to check our answer whether it's valid or not is to look at the molecular formula given and check our answer. So, okay, we have 2 oxygens, 3 oxygens. Oxygen is correct. Okay, carbon 1, 2, 3, 4, 5, 6, 7. Carbon is also correct. Let's check the number of hydrogens then. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's also correct. And the last thing, of course, to check is to see whether this compound gives us what we require in terms of getting our compound over here. So you may recall that a methyl ketone, if you do iodoform test, I2 NaOH, of course, equals, with some warming, you get RCOO minus. But over here, you can see I have 2 COOH. So the RCOO minus can be easily converted to RCOOH via protonation. Alright, so in this case, take a look. I'll use iodine in NaOH, warm, just like I do iodoform, and then I do acidification. Why? Because I need to convert the COO minus to COOH. So this is your oxidation involving step down. Okay, so if I do some mapping, okay, this could be your carboxylic acid for this, and then after you count number 1, 2, 3, 4, 5, 6, 7. Alright, and then you do mapping, okay, the pink color carboxylic acid. Alright, so that's carbon number 1, 2, 3, 4, 5, 6. Alright, so this COO minus, alright, the number 7 carbon, the CH3, if you recall, becomes your yellow PPT of CHI3. Alright, after iodoform. Okay, with that, we are done with question 1.